All right. Well, I'm gonna go ahead and get this started. That way we can complete everything on time and everyone can go to lunch. Like I said, my name is Alex Zamzes. I'm the in-house engineer and VP of technology for Belzona Houston. Today we're going to talk about everybody's favorite question, which is how long is it going to last? So in other terms, we're going to talk about repair lifetime. And in order to do that, we're going to talk about our ASME engineered repair, which is our Belzona Super App 2. So we'll start out with the overview on engineered composites. We'll look into the API and ASME documentation and standard practices, and that will allow us to assess lifetime, talk about failure modes, and then talk about inspection. So starting it out with just an overview on the composite industry. This is a growing industry, and it's actually been in play for a lot longer than you would think. I like to always give an example of something you use in your everyday life. Well, not maybe every day, but everyone flies quite a bit. The commercial and defense aircrafts have been using composites since the 1950s, according to several sources. And anything from the tail cone, you can see a graph here or a chart showing all the areas that are made of composites. Now, the reason they do this in this industry is because you're using a lighter weight material that has the same strength. With lighter weight, it's less corrosive and less susceptible to fatigue, which means we're going to use less fuel and we have ability to accommodate more cargo. On the industrial sector, which is what we're concerned with today, you might have seen the phrase FRP. That's fiber reinforced polymer. That's what you're dealing with for the most part in the industrial sector. We have whole tanks, vessels, pipes made out of composites. For the most part, they're going to be a fiberglass with an epoxy resin, like what you're looking at here. The blades for wind turbines, for example, are a fiberglass composite. And then a big industry, which is what we want to focus on today, is the repair of steel equipment. Doesn't have to be steel. Can be a composite, can be concrete. Repair with FRPs, so with composites. So the standard that we use to do all this is ASME PCC2 Part 4, Article 401, which is non-metallic composite repair systems, high-risk applications. So this standard basically put everything into one guideline so that we can use composites correctly. Because when it first came out, maybe people were just throwing it on or not using it correctly or didn't have a way to really design the system and use it properly. So this standard came out with a whole set of pre-qualification testing. All that testing gave us the variables we needed to put into the design methodology so we can determine how thick a composite needs to be, how many wraps there needs to be, and I'll get into all that later. If you're not too familiar with these types of repairs, it states what kind of training you have to do for your installers, and then it talks about where we can use these repairs, applicability, and how long they might last or what type of inspection we have to do. So I'm going to kick it off with some of the pre-qualification testing. So what we have here is a composite material. Ours, specifically Belzona Super App 2, is a carbon fiber fiberglass reinforcement sheet that is saturated with an epoxy resin. And the epoxy resin is liquid. When you mix it, saturates the cloth, and then once it cures, it forms a hard composite, similar to a cast. So the epoxy resin has certain limitations, just like the fiber itself, the carbon fiber has limitations. But the epoxy resin is going to give you your temperature resistance, your chemical resistance, and your adhesion. All that is very dependent upon your resin. So you have to do a lot of testing to make sure the resin's not going to go soft at a certain temperature. It's not going to get eaten up by certain chemicals, and it's going to stick to the substrate good enough so that it doesn't come off. Then when you look at the composite as a whole, because we are combining two different materials, that's what a composite is. We combined one material with another. So the carbon fiber is combined with the epoxy. Together, it's going to have a certain strain and stiffness, structural strength value, a pressure retention, an impact resistance. So we have to do a whole set of testing. Some of them are pass-fail. Some of them just give you a value. In the end, you can use them in the equations to determine the output of your repair. Going into one specific test that I like to show, and this basically proves to you why you would use a composite. So we have a test specimen that 85% of the wall is removed via machining. The original pipe with all of its wall should be able to hold 2,753 pounds according to Barlow's equation. The job of the composite is to make sure that even though we have 85% wall loss, if I wrap it with my composite, it can still handle the original burst pressure of 2,753. So this is one of those pass-fail tests. It has to hit 2,753 in order to prove that we're actually reinforcing the pipe. So we did, and it reached that 2,753. And then once it reached 3,065 psi, the pipe did burst, and along with that came the composite. Now, what I do want to mention here is this test is fairly difficult because you design the composite very thinly. So you don't, it's a very non-conservative design for this application. In general, you could say this is very non-conservative scenario because you would never operate a pipe at its burst pressure. And we'll get into that later. But this is one of those tests that you have to pass. So once you have all the testing, you can now start designing. So I'm going to go over designing very quickly, just a high-level overview. The first thing you want to do for designing is make sure that you have enough strength in the pipe to handle the pressure as far as hoop stress and axial stress. So what we call this is our type A equations, thin wall equations. We want to make sure that that pipe is not going to yield and burst under pressure. So that's the first thing we do. We look at the substrate. We see, okay, we have 50% metal loss, or we have even worse metal loss, or we can even say, let's assume there's no pipe there. Let's assume we're going to lose the entire pipe section, and let's put all the stress from the pressure onto the wrap. So there's different ways you can make a more or less conservative repair. But basically, the main idea is you're bringing the deteriorated asset back to its original design pressure capabilities. Nextly, if you have a leak, you want to design, hey, how much thickness do I need to contain a leak? So this is done via several equations. We have equations for circular holes, for circumferential slots, for axial slots. The main inputs to the equation are going to be your pressure and the size of the defect. And then we use the testing information we have, plug it into this equation here, and figure out how thick the repair has to be. So this equation is very, I like to say, realistic because it's based on empirical data. This energy release rate, which is in this equation here, the lambda LCL, that was obtained via testing, and we do the testing by doing leak repairs on spools. So we have a spool with a hole, we pressure it up, do several sets, and obtain that variable. So very real world application here, and also a lot of safety factors thrown in there. So this allows us to figure out how much pressure we can hold. And it has a lot to do with the composite itself, but also the epoxy resin. You know, you want it to stick a lot to the substrate because if not, if you don't have good adhesion, the fluid can escape through the ends or underneath the repair, which is what you'll see later. So then going into repair life, this is the only thing the standard says about repair life. And I'll let you guys read it while I talk, but basically it's you have to look into the repair, look into the corrosion, look into the corrosion source, the status of the metal, and what kind of repair you can do. Now I'm going to go into the next two slides of what I look into every time I put a design life on everything. So in the industry, a lot of, you see the number 20 years come up a lot. And I found a source where it says 20 years. There's another standard called ISO 24817, which is the international standard. And that does state that a short lifetime is 2 years and a long lifetime is 20 years. Maybe one of the early versions of the ASME standard has that as well. But as of now, there's nothing in the ASME standard that says anything about a 20-year repair. That being said, 20 years is normally our optimum case because that's just been an accepted number in the industry for quite a while. So to us, 20 years means everything is perfect. That means we can do the best surface preparation possible, which is abrasive blasting. If we can only do power tool cleaning, it's a little bit of a downgrade because we don't have our optimum surface preparation. If we can do hand prep only, then we can't even do compliance because we're only pre-qualified for abrasive blasting or power tool cleaning. Corrosion source. If it's external, as soon as we put on that wrap, the corrosion source is no longer there. So that's our optimum thing that we can have, our optimum corrosion source. If the corrosion source is internal, it's a bit of a downgrade because we can't stop the corrosion. So I don't see how your 20 years, your optimum case is going to be there if you have internal corrosion, unless you have really good corrosion data and you can say we're going to have this much metal in 20 years. And we'll talk about inspection data on the next slide. And going together with corrosion source chemical contents, if you have a leak or internal corrosion and you have a chemical in there that your composite cannot handle, then that's not the optimum case. You have to make sure that the chemical is not going to eat away at the resin in the composite because that can cause leakage out of the composite. So type of defect, thin walls are optimum. Um, Obviously, a lot of times we're repairing through wall defects. I know the word downgrade might scare you, but it's just we're just taking it down from 20 years. So if you have a leak, maybe we want to downgrade, not think 20 years. Maybe we want to inspect it every 5 or 10 years because now you have a more of a chance of the composite failing. And we'll get into failure modes later, but through wall is definitely more of a risk repairing than thin wall. Active leak might even downgrade you more because with active leaks, you never know what you're going to have to do to repair that. So you might think, oh, I'll just plug it with a little plug and it's done. But after you're done with the live leak, you might have a 12-inch repair on it that has compromised area because you weren't able to prep that area. So going further, inspection data to me is crucial. A lot of times that you might get an application survey report that says I have internal corrosion, this and that, but they don't have the exact data on how much metal loss they have at the moment or how much they expect in the next 5 years. And at times it's tough. Everything's in a rush, or they just have a leak that popped up and they need to get something on it quick. But having that data is going to make an optimum repair because we can dial in that design and make sure everything is appropriate for the application. Now, what we can do with no inspection data, sometimes it's not really a downgrade because we can go really conservative, assume the worst case scenarios, and go. But at that point, your other areas might be downgraded from the optimum level. Landing room. And what I mean by this is, do I have room to extend beyond the defect? If I have a hole right at a flange and I can only go 1 inch past the flange, I might not meet my axial extent that's calculated in the design. So the design is going to calculate how far I have to go beyond the defect, beyond the hole, in order to have enough adhesion and length of repair to cover the defect and work properly. Operating pressure. So theoretically, you design it for the operating pressure. So there's not really a downgrade when you move up in pressure because we're going to increase the number of layers and we're going to make sure it's designed. But however, when you look at just on a risk assessment level, if I have a drain pipe, just draining at ambient pressure versus a line at 1,000 psi, I'm going to be a little bit more cautious of that 1,000 psi line, and I'm going to set a more stringent repair frequency inspection just because of the risk that could happen with what could happen if it does fail. And the same thing with temperature. Anytime you're repairing a steam line or a high temperature chemical, you just have more risk involved with what happens if it were to fail. Also, the resin's performance is going to change based on temperature. So we have high temperature resins, but once you get above a certain temperature, the properties go down and we can't handle that. So the standard does include a lot of safety factor with temperature, and it knocks off a lot of so the resins could actually go a lot higher in temperature according to their testing, but the standard is going to knock them down just to be on the safe side. So I know that was a lot going into everything. Basically, ASME came out with the standard that allowed us to use materials like Belzona Super Wrap 2. And that has been referenced into different API standards, such as API 653 for tanks, 510 for pressure vessels, and 570 for piping. So we'll start out with the storage and start out with the tanks. This is just some verbiage from the API 653. Basically, if you're using the non-metallic composite, it has to be in compliance with the Article 401 that we use for composites. You can use it on the shell and nozzles, can be used for thin wall and through wall, and the design of the repair system shall identify the recommended service life, inspection, and maintenance programs. So basically, it's not giving you like a definite answer of these are good for 30 years, 50 years. It's just saying you have to basically do what we do on every repair. Like look at, what's the corrosion source, what's the risk, what's going on here. Now, tanks going into a tank application, I would say are some of the more easy applications just because you're not dealing with high pressure. Um, Normally, and at times you can, if you do have a leak, you can drop the level of the tank and do a good repair. But the main thing is it's just not high pressure. So pressure is really the hardest thing to contain with these wraps. And you're talking about just hydrostatic pressure. So looking at this application, this is a molten sulfur tank. And the issue was not actually the molten sulfur, it was the steam coils were leaking within the jacket, which caused accelerated corrosion under insulation. So the steam coil was repaired. So the corrosion issue was no longer there as far as that steam leak. So this is an external corrosion case, and the corrosion source was fixed. But even if it were to keep leaking, we have the wrap on top of it as well, so that would stop it from corroding. The through wall defect, that's not our optimum. Anytime you're repairing a through wall defect, you'd now have a chance for the composite to fail, theoretically. Uh, Low pressure or optimum or compatible with molten sulfur. High temperature, that's not the optimum. Abrasive blasting or optimum. So this, we gave a 10-year inspection interval. Now I want you to notice that I didn't say 10-year repair lifetime. To me, it's more of an inspection interval. And then can we get to the 20-year lifetime? The 20-year lifetime is possible for any repair. I wouldn't wait 20 years to inspect it. So to me, it's the 20 years kind of the maximum, but I would put the inspection interval less than 20 years depending on the application. So this one, since it was a leak, I would check it in 10 years and check if it's leaking. And we'll get into inspection at the end of the PowerPoint. And this is the finished repair. So going into pressure vessels, API 510, temporary repairs of pressure vessels may be made on stream by installing a non-metallic composite in compliance with the Article 401. What it says about repair lifetime is it says they should be reviewed by the engineer in preparation for the next turnaround to determine if they need to be removed and if the pressure vessel needs to be refurbished. So we have to look into the defect and is it worth removing at the next turnaround, or is this a repair that's actually superior than cutting it out and putting a new one in? Maybe you just had external corrosion and you had a little bit of pitting and you were just putting on a repair. It didn't really need a repair, but you put it on to make sure that the next turnaround goes smoother. Um, in this case here, this was during a turnaround and they actually put this repair on during a turnaround. So they did weld repair underneath this repair, but then put this on top of the weld repair just in case anything else, any other areas had issues, and also just to reinforce that area and also to isolate it from CUI at the same time. But the example I want to go into in more depth is going to be this tower reflux drum that had propane at 270 psi, had severe corrosion, a 0.87-inch nominal thickness down to 0.3. Even though it's severe corrosion, it is external corrosion, so that's optimum. Thin wall, that's optimum. Abrasive blasting, that's great, that's optimum. However, and we see this all the times, they did not want to prep the badly pitted areas because this was done with a live vessel, a live drum. So this was live at 270 psi with propane. So they didn't want to take the chance that there might be a tiny spot pinhole that might pop open once you blast this. So that area is, a compromised area. Um, However, we are going to blast, we're going to extend our blast a little bit further. We're going to cover that area with a surface tolerant material, let it dry. Once we blast, we can blast safely without worrying about popping a hole in there. Moderate pressure, so 270 psi, we'd say moderate pressure, not concerning, not like it's a 5,000 psi line or something like that. Low temperature, which is optimum. We gave this a 5-year repair inspection interval. However, we knew going into this they were going to remove it at the next turnaround, which they did. But this allowed everybody to walk around the vessel without a worry that we got a problem here. This was definitely when they uncovered this during the CUI inspection. This is one that scared them, and they really put this in so that they did not have to shut down. I have some pictures here, but this was part of our design scope, and then this is the end installation. So this allowed everybody to walk around here without having to worry about anything. Um, no more corrosion. Once they insulated it back up after the repair was done. We don't have to worry about any more CUI, and so this worked out really great for them. They were able to remove it during the turnaround. It wasn't the easiest to remove. They're not made to be removed, but they were able to do it and do their weld repair. So finishing off with pipes, temporary repairs can be done with, once again, as long as they're compliant with the ASME standard. They should be removed during the turnaround, but may remain if deemed acceptable with engineered and risk assessment. So looking at an example here, and I like to show some of the more strange examples. This might look normal, but you'll see in a second that we had to do some extra stuff here. So this is a midstream crude oil line with a defect near flange. This is what I was talking about with the landing room. So the hole, which seems to happen a lot, is right at the weld near the flange. So it seems like they had some sort of weld issues, pinhole at the weld. So we called it internal corrosion. So we actually did the wrap first just to get a nice wrap around the whole pipe. Once the wrap was done, we came back the next day and sweat blast a certain area, put some of our high build material onto the bolts, and then extended the repair in the immediate leak area so that we can get more extension beyond the actual leak. So this is what the end repair looked like. So internal corrosion, we're probably concerned that this weld might have a little bit more issues down the line, and we don't have that much landing room beyond it. But we were able to blast. It's a low pressure line, so you might get away with just getting 2 inches past the leak here because it's not really high pressure. We don't expect that pressure to pop up and try to go out. Low temperature, and we're compatible with the chemical crude oil. We're compatible. Put a 5-year inspection. I'm sure they're walking by this weekly and looking at it, making sure it's not leaking. And that's the other thing about the 5-year inspection interval. I'm sure if there's really accessible lines, your operators are going to be walking and checking on it, and you're probably inspecting it more than that 5-year inspection interval. This is just that interval where, hey, you want to maybe call us, we'll come look at it, check it out, and figure out what we need to do from here. Do we extend another 5 years? Do we add another layer? Or a lot of times with internal corrosion, you might get a leak past the wrap, so we might have to make a longer wrap, and we'll talk about that in just a second. But going into failure modes, and that's the main thing we want to avoid, and the main thing we want to be prepared for, and make sure we get those repairs going as long as they can, get you to your turnaround, get you to the wherever you need to go to. So very rare to have a failure mode, to have a failure when you have thin wall and external corrosion. Once there's nothing really that could happen at that point. I mean, the only failure off the top of my head here would be if the pipe were to fail. And the only way the pipe were to fail would be that you're operating at a pressure that the pipe couldn't handle because of how thin it is. And as we know in the industry, you have your maximum allowable working pressure, and you have your design pressure and your operating pressure. So we're always going to operate a lot under what the pipe can handle. And if you do have a pipe that's operating at really high pressure with chemicals, then there has to be a lot of inspection that goes on with that pipe, and you would figure that the corrosion get to the level where we have a big concern there. Sure, it happens, but we do have, safety processes in place that make it hard for pipes to burst. That's not a normal thing to see a pipe burst. We do see leaks, but we don't see the burst happen quite often. So if you do have a pipe where a wrap on where there's no leakage, then there's really not a lot of failure that could happen with that composite. I mean, you could see maybe like a little bit of lifted edges. Now, if you install it wrong and it doesn't cure or something like that, then that's a different failure mode. That would be a failure right off the bat. You come the next day and it hasn't cured. But there's really nothing that is going to happen if I wrap a line that's in perfect condition or a little and there's no leak in the pipe. There's nothing to fail for the composite. On the other hand, if I do have internal corrosion or a through-wall defect, so I have a leak, the composite could eventually leak too if it's not done right or not designed right. So this is the main failure seen in the industry is a leaking composite. And for the composite to leak, the pipe obviously must be leaking too. Now, one thing to mention is composites are designed to fail safe. So basically, the strength of the cohesive strength of the layers mixed with the resin is stronger than the adhesive strength of the resin. So this is the type of failure you're going to see if a composite does fail, or I should say a properly installed composite. And I know it sounds crazy to a properly installed composite to fail, but this is how a properly installed composite should fail. Right at the end, that means the fluid came out the hole, it hit that composite, and that composite said, "No, you're not coming through here," and the fluid made it out the edge of the repair. And this is going to happen at the higher pressure, um, or maybe you got a bad chemical, or you didn't prep the metal right, something like that. We have a lot of safety factor going into our designs to stop this from happening. This is part of a testing program that we did to test, where is it failing at with a certain amount of layers and all that. So possible acceleration of a leak failure, incorrect surface preparation. So if you put on a wrap with no prep, your adhesion is diminished. So that liquid is going to come out the hole and go out the end real easy. Aggressive chemicals is just going to eat away at the resin and work its way through. Poor installation quality, live leak scenario. So sometimes people do wraps and it's leaking the whole time and they think, oh, I'll just keep wrapping and keep wrapping. And they might stop it for like 20 minutes and they wrap it, come back the next day and it's leaking. That's because that liquid was working its way through the resin while it was curing. Um, so so how do we stop this from happening? Well, the first thing, just inspection and QA/QC during installation. So like the standard says, just make sure your applicators are trained and certified. We do training here. Uh, make sure they understand how to install the system. The repair must be installed per a properly designed system. So another thing we see happen is they have the product on hand and they just put on one wrap or two wraps when that line might have needed 5 wraps or 6 wraps. So, or they put it on at 10 inches, but really it should have been 20 inches. So it just has to be designed and thought through. We're always going to specify the surface prep that needs to be done, how long the wrap has to be, how many wraps you have to do. There are certain pressure thresholds where we say you're going to need a blast. Like above 500, normally you're going to want to blast because that's a good amount of pressure coming out. And then once you're done with the application, you want to inspect it. You want to come back the next day, make sure it's good. A lot of what we'll look for is look for dry spots, make sure they saturated the cloth with the resin, make sure there's no large wrinkles. So this is a carbon fiber composite, so it's not, it doesn't mold exactly like you would love it to mold. You have to really work it in, and that's what we do in our training. We show them how to use the wrap, but you want it to be tight, and you don't want any large foldovers or wrinkles that could cause air pockets, and that could cause an area that's not bonded well. So you definitely don't want any cracks, delamination, lifted edges. You can check for the hardness, and then optionally you can do a UT inspection after the installation, which I'll talk about in the last slide. So basically, we're looking, and we have a full procedure on what to look for once you how to do the installation, how to inspect it. So once you're in the field, You got a good repair on, good design, good installation. The in-service inspection methodology per ASME is the frequency of inspection should be determined in accordance with the risk assessment. So thin, and it mentions this, it has two sections, one for thin wall with external corrosion and one for through wall or internal corrosion. So thin wall with external corrosion, further deterioration of the substrate is stopped. The main inspection is just to ensure that the repair laminate remains intact and it's not delaminated and it's just there. You go there, check on it, make sure there's nothing going on, there's no cracks in it, hasn't debonded, forklift hasn't hit it, stuff like that. Through wall or internal corrosion, further deterioration of the substrate or growth of the defect may still occur after we install the repair. So to extend it after that repair lifetime or inspection interval, we want to get some sort of X-ray or UT or corrosion data to confirm that, hey, we designed for a half-inch hole 5 years ago. Is that hole still a half inch? Or is that hole now an inch? Or, hey, we designed this 10 years ago, and at that time we had 10 inches of corrosion. Can we do an X-ray now and just make sure that the corrosion hasn't extended past this area? So that's where a more quantitative inspection comes into play. So going over what you're going to look for the visual inspection, you're going to look for leaks. Inspector should know the location of a leak. So is it in the middle of the repair? Is it in the end of the repair? Really, if you see a leak in the middle of the repair, you're thinking something happened here, installation or process wise. Note for cracks, look for delamination. Uh, if you see the edge lifted, you can get a putty knife underneath and try to rip it off and see if it's just an adhesion issue we got going on. You can do a tap test. That's you lightly tap the composite with like a hammer, and you can see the sound is like more of a ding when it's bonded to the steel. It's almost like you're hitting the steel, and if it's not bonded to the steel, it sounds very hollow. So a tap test is a great test. You do that after installation and during your inspections. Make sure that that composite is bonded to the steel, and then environmental wear. Make sure there's nothing on the surface. Maybe some acid has been spilling on it because you could be wrapping a pipe that's in a secondary containment for sulfuric acid, and it could have acid spilling on it for a couple years. So that you never know what the scenario is, but there's a lot of things to look for in your visual inspection. Now, your more quantitative inspection is going to be an X-ray or a UT. X-ray will see right through the composite, and your limitations are basically whatever your limitations are on X-ray is going to be your same limitations if you have a composite on there. Talking to some different inspectors, they said pipe size, acid size is what gets you with the X-ray sometimes. UT inspection, which is how they inspect a lot of the plane equipment and aerospace technology, is mainly done with the UT inspection. There are ways to shoot through it with pulse echo or low frequency techniques. We've worked with several UT inspection companies, and they've done some tests with composites and our composites specifically. There are some things that, it makes it tough. So you want your surface to be real smooth, because if there's any, normally they're using a system that's kind of like a robot and it goes around the pipe and test it. And if there's like a little bump on the composite, it'll give you a false reading and tell you that you have a hole there. So sometimes the composites come out perfect. Sometimes there is a little wrinkle in there that's not, just a resin wrinkle. So surface flaws and irregularities can create inaccurate results. One of the main things to consider with the UT inspection also is you really want to get a reading of the metal substrate before the repair. That's going to give you your metal reading. Then you get a reading right after you install the repair. That's going to give you your repair plus substrate reading. And now you have the base to inspect it in 10 years or 5 years. Because if you only do one in 5 years, you don't know if that's like when you get a no reading on the UT, it could mean two things. It could mean a hole in the pipe, or it could mean a debonding of the composite. So it could mean an air pocket. So that's why you want to do your UT right before you install it, It's going to map out everything, show you where the holes are, where the low spots are. You do it right after the repair. Now you got a reading here that says no reading. That means you got a little air pocket there. Okay, I know I got an air pocket here. When I do it in 5 years, I have the same air pocket. So, that's the UT is definitely a more, you have to plan it out. And figure out, is this worth is the risk assessment worth the extra inspection to do this? So I know that's probably a little longer than the usual one. Um, I appreciate everybody joining in. And if you have any questions, just shoot away, take yourself off mute, and let's talk.
Hey, there's one in the chat, Alex, from Michael Faulkner.
Okay, let me open it up. Some years ago, it was thought that wraps must go all around the cylinder. This is very important. I still find myself informing others about it. When did it change? So that's been a while. You can do patch repairs. That's definitely been going on for, I mean, definitely more than 8 years, because I've been doing patches since I started with Belzona. Um, there's a statement in the ISO 24817 standard that states that any diameter over, they have it in millimeters, but 600 millimeters, you can go with the patch method. And basically, we're going to reinforce that area wherever we stick to, we're going to reinforce it. And as far as leak repair, the leak repair is pretty much based on adhesion and the strength of the layers built up. Um, so you don't have to go all the way around. Now, if you have piping, we normally go all the way around just because it's easier to do a wrap on piping. But yeah, for like a pressure vessel or something like that, you wouldn't have to go all the way around unless the whole area was compromised.
Does the number of layers decrease if you do go all the way around?
No, it's actually calculated in the same exact manner. Sometimes what I'll do is I'll make it so if I calculate with a wrap that I need to go 5 inches past the defect, if I'm doing a patch, I might go a little bit further just to, because I know I'm not going all the way around it. So I might increase the length a little bit as far as that. Since we're using less product anyhow, it's still less labor and product. And we haven't had any issues with doing the patches. Um, we even did tests when I was back at Belzona. We wrapped our 4-inch pipes that we do our pressure testing with. We did patches instead of going all the way around, and we got the same pressure retention with doing a patch versus wrapping around the pipe.
Is the ability to do a patch instead of a wrap all around, is that specific to the Super Wrap 2, or do all of your products have the ability?
Yeah, all of our products have that ability. The pace grades, same thing. We do patches on vessels all the time with those, the tanks, and we do also the plate bonding. If you've seen us do that before, where you do a plate, you bond a plate with the Belzona and then you patch over it. So yeah, the patching is definitely a big part of our um, process, because you have a 200-foot diameter tank. I'd love to wrap it, but I don't think it's feasible, especially with
Gotcha.
one
Thank
little
you.
hole. Yeah, no problem. Any other questions? So I think Brianna put something in the chat that if you've registered online, we have your information for the continuing education credit. If you did not register and you want your continuing education credit, put your email and name in the chat, and we'll get you the continuing education credit so you can submit that to get all your certs up to date. Any other questions, comments? Well, I appreciate everybody coming in and joining us for this webinar. The next webinar will be next month. It's the first Wednesday of each month. So look forward to seeing you guys there. And if you have any topics that you have in mind, feel free to email us and say, hey, can next month's webinar be about this? And we'll make it happen. So have a good one. Stay safe. And thanks for joining in.